if you look at the location T3 and T2, and I bring T3 closer and closer to T2, then this angle of alpha will increase. And I can go to the extreme that I bring T3 almost right at T2. The angle of alpha will then be tangential to this point. This will then be my angle of alpha. And now you will understand how we define the instantaneous velocity at time t, which is different from an average velocity between two time intervals. The instantaneous velocity, v, and I pick a random time t, equals the limiting case for x measured at time t plus delta t, minus x measured at time t, divided by delta t, and I do that for delta t goes to 0. So think of this as being T3 and this as T2. I bring T3 closer and closer and closer to T2, and the time between them then goes to 0. And this is something that you undoubtedly recognize. That's the first derivative of the position versus time. And now comes an equation, which is one of the very few that I want you to remember. And this could be larger than 0, this could be 0, and this could be smaller than 0. If the angle of alpha, the tangential, is positive, then it is a positive value. If it is negative, however, when you hear, then it is a negative velocity. And if the angle of alpha is 0, then the velocity is 0. So if we now look at this plot, we can search for the times that the velocity is 0. So you have to look for the derivative being 0. That means the angle alpha being 0. Clearly here, the velocity is 0. Right here at this turning point, that means when the object is here, it is 0. When the object is here, it is again 0 at this moment in time. Again, the angle is 0. And it is again 0 here. So those are the times that the velocity is 0. What are the times that the velocity is positive? Well, it's positive here. Velocity is positive here. Still positive, positive, becomes negative. Negative, positive, 0, negative. So that's the definition of the instantaneous velocity.